Give me a second.
Seems to have happened. Okay, so welcome to everybody who's joining us via YouTube to this Astronomical Society of Glasgow lecture. This is the Tannahill Lecture, a very special lecture in our calendar. I'd also like to remind you that if you're not members of the Astronomical Society of Glasgow, members, not only do they enter the Zoom meeting for these lectures, and so they can display themselves in video and be there less virtually and well, more virtually, depending on how you view it. But also we have beginners group meetings, imaging meetings, and we're starting up observing meetings and members observing nights and an away weekend for members. All of these things take place throughout the year, and hopefully if COVID carries on receding, we'll be able to resume more normal activities later this year. So if you're not a member of the SG, please do consider joining. It's not very expensive, and as you say, you get access to all these other things. So, but our main reason for gathering here tonight is to welcome our speaker, Professor Andy Lawrence, Regius Professor of Astronomy. And he's come virtually over from the Institute of Astronomy from the University of Edinburgh, and he's giving our Tannahill Lecture tonight. And it's, well, it's about why the night sky matters and how we might lose it. For those of you that aren't acquainted with Andy, I'm sure many of you will have at least heard of him. His research area covers quasars, observational cosmology, survey astronomy, and the Virtual Observatory. And he's recently become interested in the idea of space environmentalism. And you can read more at his website. The link's on the website, but it's andyxlastro.me, but you'll get the link in the website. So without any further ado, can I ask Andy to tell us about the sky, why it matters, and how we might lose it?
Thank you very much. So I guess I'll start straight away by showing my screen. Let's see if that works. There we go. And then I'll play the presentation. Right, can you confirm that you can see my slides and hear me okay?
That looks good.
Yep, we can.
Okay, very good. Well, thank you for having me here. I was going to say in Glasgow. I know I'm still on my sofa in Edinburgh, but it's a real shame not to be in Glasgow. I do love traveling to Glasgow. So it's a shame not to visit you all and drink a beer afterwards and so on, but there we go. So my topic today, the sky, why it matters and how we might lose it. Now, warning, I do have about 8 million slides, but I'm going to whistle through them very quickly, so don't panic. But if I start to drift, you can shout at me. Okay, the talk's going to come in 3 parts. Part 1, which is the longest part actually, is astronomy useless? Part 2, the threat to the sky. And part 3, what is it that we can do? What can be done about this threat to the sky? Okay, so let's get straight in with part 1. Is astronomy useless? Now, I would imagine that the answer of members of the society to that question will be fairly clear. They'll all say, no, of course not. But I bet, you know, you're all asked this question and all the time by sort of, you know, relatives and friends and so on. Now, isn't it all like a waste of taxpayers' money and so on? So the answer to that, I think, is no. But let's just kind of look into this step by step. All right. So there's no doubt that the objects up there in the sky that we study as astronomers, whether professional or amateur, are very beautiful, and also that they're intellectually fascinating. But you might think, well, but this study of the sky, it is beautiful and fascinating, but isn't it fundamentally useless? I mean, you know, compared to the economy or technology or the National Health Service and or even, you know, our daily lives, isn't it really just a kind of frothy entertainment? And I think the answer is no, and I'm going to try and convince you why. And if you already believe it's not useless, hopefully this will arm you with some points to make with your friends in the pub. Okay, now I'm going to start with this sort of historical roots of this issue, and then come up to modern times in a little bit. But let's start deep in history, because by far the biggest reason, the real biggie historically, is agriculture, feeding ourselves. If you want to know when to plant and when to sow, you have to know when you are in the cycle of the seasons. And to do that, you have to watch the sky and understand how it changes. So studying the sky was crucial to ancient humanity in order to develop agriculture. Second biggie, divination. Now, this is where I know a lot of astronomers are going to bristle at this, saying, oh, astrology is nonsense. We don't want to hear any of this. And I think that's a big mistake, actually. Astrology, historically, is undoubtedly very important to civilization and humanity. And you can see it as a kind of proto-science. I mean, what did astrologers do? They tried to see patterns in the world, to use those patterns to try and understand the world, to predict it, and to control it. Now, all those things are exactly true of modern science as well. So, of course, today, any sensible person sees astrology, let's say, as a failed science. So we don't take it seriously anymore. But those origins are important for humanity are just undoubted. Now, why am I showing you a Chinese image top left there? And what's the Crab Nebula got to do with this? Well, probably many of you know this, but the Chinese were particularly obsessed with monitoring the sky for astrological purposes, and especially looking for things that changed in the sky as especially important portents of events and so on. And in 1054 AD, Chinese court astrologers saw a new star in the sky. Now, we know now that what they saw was a supernova. And if you look at that spot today, what you see is the Crab Nebula. What's left behind is expanding shreds of gas left over from that exploding star. So that's a bit of a digression, but fascinating, of course. That's divination. Next up, navigation. Now, if you're exploring the world, if you're traveling around the world and you've got to do a lot of that over water, it's very hard to know where the hell you are. And studying and understanding the skies and how the positions of the stars change with time is absolutely crucial to this. So first, most simply, if you know the height of stars above the horizon, and you measure them and they're not what you usually expect, then from that you can work out what your latitude on the Earth's surface is. Longitude's a little bit harder. To know where you are in longitude, you measure the rise and set times of some particular star, and you compare that to what you're expecting when your boat left Liverpool or whatever. So to see that difference, you've got to know what is the time in Liverpool now. And to do that, you need a clock that works on board ship. So, of course, that was a great mechanical advance, but that enabled observations of the stars to give us longitude. Now, talking of time, during the 18th and 19th centuries, Western civilization became increasingly obsessed with time and precise timekeeping. For example, the importance of the railways. If you're trying to catch a train that left London at a certain time and you're sitting there in Bristol, then in Bristol you have to know what the time is in London. So somehow you've got to keep your clocks tied together, synchronized. And in the 18th and 19th centuries, that was the job of astronomers. That's why the government were prepared to pay for astronomers. That was their job. You calibrated the clocks according to the night sky. So on the left here, you see this is the Nelson Monument in Edinburgh on top of Carlton Hill. And what you see there is the time ball started by my predecessor, Charles Piazzi Smythe. Just before 1 o'clock, that ball gets lifted up to the top of the mast. And exactly 1 o'clock, it drops. And then the sailors out the Firth of Forth know that it's exactly 1 o'clock and can reset their watches. And of course, the astronomer had his own clock to do that, calibrated according to the sky. Now, here's the thing. So it's all about synchronizing clocks, okay? And if you've got lots of clocks and you want to keep them tied together, you need at least one clock that you know you can trust. That one clock is the rotation of the sky. So absolutely crucial to the development of Western technology and civilization. Okay, that's the big historical things. Now when we've moved up to modern society. So we'll look at some fairly social things first, and then we're going to look at science and technology. So you might say, well, all those things are in the past, but they're kind of irrelevant now because we've got atomic clocks, they all work, you know, and we've got GPS and satellites, and so that's all gone. Well, yes and no, but there's still very important things about astronomy today. First of all, a sense of perspective. So, you know, we think it's quite a long way from Edinburgh to Glasgow, and the Earth is even bigger. But of course, the Earth is much smaller than the Sun, and you can fit 1 million Earths inside the Sun, as in this beautiful model made by Stuart Lowe. It's pretty accurate, by the way, that model. And understanding this sort of thing gives you a perspective on the world you live in, which I think is important for psychology and culture of humanity. Then we look up at the sky. I'm sure you recognize the plough, and knowing how far away those stars are, again, puts things in perspective. But of course, most of the stars we can see are much further away than the plough. On the right there's a lovely picture taken by Gordon Mackey from the Caithness Astronomy Group. That's the Milky Way, arcing diagonally across the sky. And when you stare at the Milky Way, if you lie on your back on a nice summer's evening staring at the Milky Way, you can really imagine that you can feel in your bones that you don't live in an infinite sea of stars, you live in a flattened disk, and that's what the Milky Way is. And you can look at it and feel that. And I think that's really quite important. Now, down at the bottom there's a part of a map of the Milky Way made with infrared detectors made by myself and my group with a telescope in Hawaii. There are very, very large numbers of stars. And this, again, really puts things in perspective. So here we are scanning across a small section of the Milky Way. It is awe-inspiring. There are billions of stars. So getting your life and our civilization into perspective. So that's some perspective. Then there's inspiration. There is our fantastic new astronomer royal for Scotland, Catherine Haymans, and she's helping a school child to make glitter galaxies at our open day at the Royal Observatory. So that's, and you know, inspiring the kids is great. But it's not just primary school children. Astronomers are important to big kids and training at university too. So here's the thing at the top there. This is a previous PhD student of mine in the control room of the William Herschel telescope in La Palma. But we don't just teach astronomy. As astronomers, we're a breed of physicists. So we teach maths and physics and technical education. And we churn out thousands and thousands of trained people who move into society, most of whom do not become astronomers, but they go out with a better understanding of the laws of nature and how to apply them. And so, again, I think this is undeniably very important. Okay, so that's very general kind of social issues. What about science and technology? Now, you might be tempted to think, well, astronomy is a kind of application of physics, so it's a kind of frothy frippery, a sort of entertainment done with physics on top of the core of science and technology. Well, that could not be more wrong. Historically and today, astronomy is bound up right in the center of the development of science and technology, which underpins the modern world. So here's a historical example, Newtonian physics. So did Newton develop his physics from watching an apple drop in Woolsthorpe? Well, maybe, but more important, what we do know is that he came up with his theory of gravity and all the associated dynamics, the whole of Newtonian physics, by trying to explain the orbit of the moon. And his big thought was, well, the laws of nature have to be the same up there as they are down here. Can I make it all make sense? So that was crucial to Newtonian physics, which then has dominated our understanding and our practical application and our engineering ever since. Moving into the 20th century, what's dominated the transformation of our civilization has been quantum mechanics, the understanding of atomic physics. And for good or ill, this determines, our understanding and our application of electronics and energy and bombs, just everything. The transformation of our world is complete. Now, core to the development of atomic physics and quantum mechanics was trying to understand the stars, both the spectra of stars, things like the Balmer lines and so on, but also worrying about how the sun burns, where its energy comes from, which is, of course, nuclear fusion. Now, you can't say that we would never have solved those problems without addressing astronomical issues, but they were certainly core to the whole problem at the time. Historically, that's just a fact. So is that going to happen again? So right now, astronomers are obsessed with what seems like very esoteric things like dark matter and dark energy, trying to explain how galaxies rotate. They seem to be spinning faster than they ought to, the expansion of the universe and how it's changing with time. And these problems lead us to these weird ideas of dark matter and dark energy. Now, right now, that is quite esoteric. But I think most physicists believe that we're probably not going to really solve those problems until there's another kind of transformation of physics. And when that happens, the effect on our technological civilization is very hard to predict. It could easily be as transformative as atomic physics and quantum mechanics, but we don't know yet. Okay, but it is once again being driven by trying to understand things out there in the sky. Okay, the economy. So you've probably heard that that's the James Webb Space Telescope, of course. And I'm sure lots of you were very excited, as we all were, and tense with all that sort of gradual unfurling and so on. Now, you may have heard that it cost $9 billion, which it did, and it cost rather more than it should have done because there were so many delays. But that's a lot of money. Now, when a big project like this costs billions of dollars, is that spent on people like me? No, it is not. Maybe I'd like it if it was, but I wouldn't really. That nearly all of that money goes out to industrial contracts for people who build the stuff that we ask for, but they build it. So it's part of funneling money from the government through into high technology companies and keeping companies in Britain, America, and Europe competitive. So it's actually really productive for the economy. Now, whoops. Went too fast there. Let's go. Ooh, no, back. There we go. Now, sometimes this is done by us being what's known as a demanding customer. So the Chandra X-ray Observatory, which has been up for a few years now, but another great earlier NASA flagship, wanted to do spectroscopy with X-rays, and they wanted diffraction gratings, like we have diffraction gratings in optical light. And they said, all right, but to do this, we need incredibly fine rulings on the diffraction grating. So they went to companies saying, well, we need the diffraction grating, but we need the rulings to be separated by 100 nanometers. And of course, those companies would giggle. Say, well, are you serious? And they said, yeah. But they responded to the challenge and it was delivered. So extreme technical challenges can drive industry. Another nice example, a more European one in this case, is gravitational wave astronomy. The future of that is in space. And to do that, you need spacecraft for which you know the relative positions incredibly accurately, and to keep them there and not wobble about too much. That's technically extremely challenging, so-called high precision station keeping. But when that problem is fully solved, it's going to be very important for all sorts of other applications. We're very good at being early adopters in astronomy as well. So, the CCD camera was invented at Bell Labs, but astronomers were amongst the very first people to turn those devices into working systems to make cameras. Likewise, although our particle physics friends invented the World Wide Web, one of the very first few websites in the early 1990s was at the European Southern Observatory. So we're early adopters. We also quite often do classic spin-out. So amongst the sort of suite of technologies that are necessary to make Wi-Fi work, that we all rely on every day, especially in the pandemic era, several of those technologies were developed specifically for radio astronomy. And there's John O'Sullivan, one of the people possible. An example closer to home is Blackfoot Analysis. There's a company in Edinburgh that work on data compression and medical imaging, and they've been growing rapidly recently. They're quite a success. But that grew out of work at the Royal Observatory by Alan Heavens and Ben Panter, who were developing data compression techniques for analyzing sky surveys. And that's where it came from. So yeah, again, so what might happen next? Well, who knows? But here's a little guess of mine. There are people developing things called kinetic inductance detectors, various places, but especially in Santa Barbara. And this could make photon counting detectors, detectors which can measure individual photons in the millimeter range, in the sort of high frequency radio range, which has been unheard of before now. So very exciting. It will be very good for astronomy, but it's pretty certainly going to be important for other applications as well if it works. Okay, last but not least, in the why is astronomy not useless? Why is it important? A new and growing thing is planetary protection. So now by this stage, I'm sure we've all seen Don't Look Up, and opinions are divided, but I loved it. Now, of course, we know it's not really about astronomy. It's a metaphor for climate change. We know that, but still, it's still quite fun seeing a movie about a giant rock heading towards the Earth it might turn us into the dinosaurs, i.e. wipe us out. So we know that this happens every so often, not too often, but there's Meteor Crater. We know this happens. You remember back in 2013 that the Chelyabinsk meteorite that broke windows and injured people. So it happens. So we're wise to check out these potential killer rocks. Now, how do you do this? You do it with wide field telescopes like this one here, Pan-STARRS in Hawaii, and you make little movies or repeated images of the same bit of sky. And you see that most of the stars are staying in the same position relative to each other, but you see this moving object. The movie's been recentered on the thing that's moving, confusingly, so it looks as if the stars are moving. But of course, it's this object here which is actually moving. So that's how you find near-Earth objects, because very distant things don't move much on the sky, and close by things are moving. So that's how you find them. Okay, so that is the end of part one. Hopefully it's either convinced you if you were a skeptic, or armed you with arguments that you can use in the future. Why astronomy is important. and some of those arguments everybody knows, and some of them are less appreciated or understood than they should be, I think, especially the fact that we actually contribute to the economy rather than just spending taxpayers' money, because we're a route by which government money is funneled to the kind of industry they want to develop. Still, very few people understand that point, but it's very important. And it is, people in government understand this is why they're willing to give us money. Otherwise, they wouldn't. So that is important. Okay, so astronomy is important, and we do all love it, and it is fascinating, and the objects are beautiful. So what is the threat to the sky? Now, there's two threats. The first one I think is actually the worst one, but I'm not mostly going to talk about tonight. So this is the one that people have known about for years, and it's gradually got worse. And as amateur astronomers, you're extremely well aware of this. It's the brightness of the night sky and how it makes it impossible to see the stars because the sky is so bright. Light pollution. So this picture here shows a kind of double sort of climate catastrophe, if you like, or environmental catastrophe. This is taken from Mount Wilson, just outside Los Angeles, an observatory that early in the 20th century was the source of many extremely important scientific discoveries. And now you cannot do astronomy from there at all, because you can see here is Los Angeles and the lights of LA just scatter up into the sky, and you really can't see anything. But the second thing you can see here is this is the mountainside on fire, and those fires are happening more and more often around LA. Now, as I said, this is actually a very, very bad problem. But I'm not going to talk more about this tonight for several reasons. One, it's relatively well known. Two is that it's not my specialism for me to explain to you. I reckon you should learn more about this, I think. And if you find someone from the International Dark Sky Association to give you a talk, it would be really good. And I'm sure you all know about the Dark Sky Park and Dumfries and so on, and that would be so that's all happening. But also, this is an incredibly hard problem to solve, because the fact that the night sky is polluted with light is of this scattered light is to do with the entirety of modern civilization. It's a real juggernaut that's very hard to stop. But what I'm going to talk about next, satellite pollution, is suddenly happening, very worrying, but also, I think, potentially solvable. It's going to be hard, but it's potentially solvable. Okay, so here's the other problem, being photobombed by satellites. Now, unless you've been living under a stone for the last couple of years as amateur astronomers, so I don't know about the YouTube audience, but this certainly will apply to the society members. You'll have heard all about this, and that our images suddenly, every so often, have streaks going across them from bright satellites. And there's an individual example taken by a colleague of mine working on the Rubin Observatory in Chile, and he was trying to take a selfie of himself with his camera. And up there's the Starlink logo there, and I'm sure you've heard that this is the major problem. Now, I should say, by the way, it's not, in the long term, they're not the big problem. It's who comes afterwards. But we'll come to that in a moment. Now, it's not just professional astronomers; it's amateurs too. Here is an amazing picture taken by Raphael Schmall, amateur astrophotographer in Hungary. And that is the star Albireo. It is no, where is that? It's Beta something. Is it Cygnus? Beta Cygni? Someone can tell me later. Anyway, yes, I think it's Beta. Anyway, it's a very well-known bright star. It's actually a double star, close double that amateurs often love to look at. Anyway, there's all these Starlink satellites streaking across the image, and it looks as if someone's put Albireo in prison. it's not just Hungary, here closer to home. Just a few months ago in Edinburgh, here was a picture taken by someone from your sister organisation, the Astronomical Society of Edinburgh. Andrew Farrow took this picture, just trying to take an astro photo, and suddenly there were a bunch of Starlink satellites streaking across the field of view. You might think, well, okay, we've got to do astronomy from space now. I know that's no good to amateur astronomers, right? But maybe the professional astronomers can just go into space. It's not obvious that helps either. At the top there is an image taken by the Hubble Space Telescope about a year ago. And a Starlink satellite passed quite close to the Hubble Space Telescope. I say quite close, maybe 100 kilometers, but that's enough for it to make a really bright streak. Out of focus, fat, extremely bright. Okay, so maybe we have to give up on optical astronomy and do everything with radio astronomy. No, that's even worse, actually. The thing about these satellites is they need to communicate with the Earth, so they're all beaming down radio signals, and to our sensitive radio telescopes on the ground, it's like an extremely loud noise. It's a bit like you're sitting in the living room and you're thinking, do I hear a mouse squeaking? But you can't tell because the kids have got the TV on really, really loud and they're shouting at each other, so you can't hear a thing. Well, it's like that. The signals coming down from Starlink satellites compared to the things we're trying to detect in the radio sky are absolutely deafening. So it's really bad in radio astronomy as well. Right, you say, well, you know, there's been satellites for ages and ages. What's new? Well, the satellite population is really taking off. On the left at the bottom here, this is a plot of the active satellites versus time. Not the total number, because there are lots of kind of defunct satellites up there as well. This is number of active satellites versus time. And it's been continuously increasing. But in the last couple of years, it started zooming up particularly fast. And you can see this on the right here, because the blue curve is everything except Starlink, and the red region is the Starlink satellites, and they're taking off faster and faster. So suddenly, and by now, that picture is about from my book that I'll tell you about in a moment. It's a little bit out of date at this point, that graph. And now the Starlink satellites have doubled the number of active satellites in the sky in the last 2 years. But it's not just Starlink. They're building this so-called constellation of satellites, and now suddenly everybody's getting into the game. The Canadians, Facebook, Amazon, China, Russia. Now, just a while ago, there was, various people have done this, but this is a number I've quoted often, a study looking through the applications made to various licensing agencies. The estimate was that it looked like by 2029, there'd be 100,000 satellites, compared to 2 years ago, 2,000, this year, 4,000. Okay, but it could be 100,000 by 2029. Now, that's also quite out of date now as well. For instance, there's been an application by a single company, a bit speculative, I'm sure, but there's a real application to launch 327,000 satellites in a single constellation. So it could get absolutely enormous. And certainly Starlink have permission at the moment to launch 42,000. So it's really taking off. So this is what I meant by it not being just Starlink, but what everybody else jumping on the bandwagon. Now, of course, they might not all happen, but they might, which is the point. Okay. Now, suppose we take that 100,000 figure. What does it mean? To put this in perspective, suppose you're looking at the sky with a pair of binoculars with a typical 7-degree field of view. Now, at the moment, if you lift up your binoculars and look at the sky, you probably have to wait a minute or two before you see a satellite drift across. But you'll see one. But by 2029, if this prediction is correct, every time you look through your binoculars, you will on average see 10 satellites in your binocular field of view. They'll take about 30 seconds to cross your field of view, and there'll be some more coming in. That's what the experience could be like for stargazers and amateurs. For professionals, we take the Rubin Observatory, our big new mission that's going to survey the sky. There could be, in every Rubin Observatory image, there could be something like 10 streaks. And to radio telescopes, which kind of look at the whole sky at once, in their local bit of sky, there could be hundreds every time they look. So it could be really, really bad. And this is what we're really all frightened of, I think, scientifically, but also culturally, is the possibility of low Earth orbit advertising. Now, this is not just a kind of fantasy or scaremongering. This is a promotional image from the website of a real company that had a proposal to link up with a soft drinks company and do formation flying of satellites to have an advert in space that could be seen by millions or billions of people at the same time. Now, they didn't get permission, I'm glad to say. And in some countries, there's laws against that, and in some there aren't, and it's a very difficult area. But it could happen unless we make sure it doesn't. Now, it's not just the live satellites, it's also all the junk that's out there. So I'm sure you've been hearing a lot about recently, suddenly becoming much more an attention because of the Russian anti-satellite tests that produced fragments that were a threat to the International Space Station. So here's a plot that shows the growth in time of all the objects in space, all the little bits of junk. Now, here is that same plot again of the active satellites with its sudden kick up in recent times. These are the dead and leftover bits, and this is all the debris, and this is everything added up. Now, you see there's two big jumps here in this graph. This is a Chinese weapons test when they blew up one of their own satellites. And this is from the collision of an American satellite and a Russian satellite that smashed both of them into smithereens. And now, by the way, this number, like 20,000 or so, is not everything. It's just all the things we can actually see with optical or radar telescopes and track. The total number of bits of debris out there is more like 1 million. And it's growing and it's getting worse. So here's a little plot that I made recently for a paper that will be coming out in Nature soon, which shows a sort of map of where everything is in low Earth orbit. So along this way is the height above the Earth's surface. The vertical axis is kind of just the azimuth, round the orbit, but it's a bit artificial. So round about here is where the International Space Station lives, really quite low. These two thin stripes here is where all the Starlink satellites are, quite concentrated in thin regions. These ones here, this is where the OneWeb satellites are. Most of the rest of these things are dominated by leftover bits of junk. These black dots here, these are the fragments that came out of the recent Russian anti-satellite test, which have been gradually spreading through orbital space. So the point is that you can see they overlap where the International Space Station is. They also overlap where the Starlink satellites are. So this increase in junk is putting the Starlink satellites themselves at risk. It's a very worrying problem. Now, why the hell is this happening? Why are all these satellites being launched? Now, you've probably heard that it's about connecting up the world with having satellites which can get internet to remote areas. Well, there's a little bit of truth in that, but not much. Even with sort of 42,000 satellites, Starlink will only be able to sort of provide internet to a few million people. It's not going to provide internet to everybody in Africa and so on. It'll improve things a lot in rural America. I think it really will do that, and it will make them lots of money, but it won't connect up the world. That's not really how it works. And we can talk more about that later if you like. So what's driving it, and why do they need so many if it's not having enough to join up the world? It's really, I think, mostly about latency with delay time. Now, most of your life, you worry about bandwidth, how fast the data comes through, you know, whether your video is juddery and so on. But sometimes some people want a very short delay time in the signals. So, for instance, if you're playing a real-time game, doing sword fights with people in Kazakhstan or something, you know, then you need the to and fro reaction time to be as short as you can manage. So that's one example. The other one is high frequency trading of finance. You know, banks competing with each other want to get the news about stock prices changing milliseconds faster than the other guys, and these satellites can do that for them. Let me explain why. So there's been internet satellites for ages, but most of them have been high up above the Earth in so-called geostationary orbit. Now, as this upper picture shows, if you're in one of these high orbits, the great thing is any one satellite can beam down to quite a large fraction of the Earth in one go. So one satellite can serve lots of people. But this delay time, the to and fro bouncing of the signal, you can get a quarter-second delay. And most of the time that doesn't matter, but sometimes it's very annoying. So you can get that down to a few milliseconds if you go into low Earth orbit, more like the sort of orbit that the International Space Station is in. And you can have to and fro delay times, as I say, of a few milliseconds. But the trouble is then, as this diagram shows you, a satellite very low down then can only see a small bit of the Earth. So if you're going to provide coverage all over the Earth, you need thousands of satellites in a sort of network, as is shown in this figure here. So that's what it's about. By the way, just briefly, I think the right answer to this that's been done by some other companies like SES, done in the O3B system, is you have something a bit middling, about here somewhere, where the delay is not too bad, but you don't need 50,000 of them. Okay, so end of the technical explanation. One more thing, just getting back briefly to this light pollution versus satellite pollution. So there is one way in which the satellite pollution is worse. The light pollution, bad though it is local. So you can at least if you're a professional astronomer, we can say, well, we're going to have to build our observatories in distant places. We're going to go to Hawaii on top of the volcano. We're going to go to a distant mountaintop in Chile. When we found these really dark places that also have superb seeing and so on. So that's where we're going to put our telescopes. Expensive but necessary, and we share it amongst tens of thousands of astronomers. So that's okay. So that's what you can do. The pollution is local. Satellite pollution, the pollution is global. You launch a satellite in California, an hour later, it's flying over France or Namibia or wherever. You cannot escape. Okay, it's everywhere. It's just a global pollution. Right, so that's the end of part 2. And now finally, part 3. Okay, what is it we can do about this problem? Assuming, like me, you're a bit hot under the collar about it and would like it not to happen. Just pausing there, even amongst astronomers, it is of course possible to say, astronomy, tough. Internet for everybody and fast real-time gaming, more important, mate. Tough luck, right? So that could be a real attitude, but it's not mine. Okay, so what can we do? Let's step through some options. Well, it should be indeed just roll over. Even if you don't think, well, playing League of Legends with my friend in Belgium is more important than understanding the universe. Even if you don't think that, you could easily think, this is a financial juggernaut. There's powerful forces here. It's not going to happen. Just give up. It's very sad, but give up. Well, I think that would be the wrong thing to do. Second possibility is to protest. So the classic way of doing that, of course, is with petitions. And there are two petitions, one aimed at professional astronomers and one aimed at the general public. And so the URLs are there. Excuse me. Back in control, I think. So you could certainly, I'd be very happy if you go and sign those and beef them up a bit. But my suspicion is that's never going to be big enough to make a real difference to make politicians care and so on. It helps a bit. Engage and mitigate. Now, this is the attitude of most of my professional colleagues, where, so we've been having, over the last 2 years, lots of technical meetings amongst astronomers about this problem and what the hell we're going to do. And the International Astronomical Union, the IAU, has just put out an opportunity to, calls for set up a new center for the protection of the dark sky for people to study it. Now, at those meetings, typically, we get people from SpaceX, OneWeb, and other satellite companies to come along and speak to us, with the idea being, well, we're not going to solve this by saying they shall not pass. We need to work with them and say, look, this is really bad. Can we work on this together and see what we can do? So what are the sort of things that people have talked about? Oh, and although the big bosses so Elon Musk doesn't come to these sort of meetings, right? But his engineers do, and there's some really good people. So what are the sort of things that have been discussed? Well, maybe we can change the albedo or the reflectivity of the satellites. In other words, paint them black, right? So they don't reflect as much light. That's running into a bit of problems because when you do that, actually the satellite tends to warm up. So that's probably not going to be the solution. But SpaceX in particular have done experiments with that. They made a thing called DarkSat to see how much difference it made. The other thing you can do is try to understand the three-dimensional structure of the satellite, and as it rotates, the reflected light that you get, which is causing all the problem, it's not constant. As you rotate, you get sort of glints. It suddenly goes whoosh, flash bright and then off again. And if you understand the satellites better, you can try and predict when those glints are going to happen. You could also maybe make sure that the satellite companies publish accurate orbits, so we can try and predict when a particular batch of satellites are going to be flying over an observatory and think, right, we'll shut down the exposure for 5 minutes and come back or something. Okay. Another thing for the radio astronomers is when the satellites know they're flying over a radio observatory, then they can redirect or switch off their beams away from the observatory. And we can develop fancy new software to try and take the problem out. Easier said than done, by the way. But this is the point. These are all quite interesting ideas, and around the edges, the satellite companies have been quite sort of happy to talk to us. But all these things take time and they take money. So you have to ask, firstly, who's paying for that? And secondly, why should it cost us all this if it's really not necessary? So we absolutely should carry on with these conversations, because if we don't have dialogue, you don't get anywhere. But I think the dialogue is not all we should do. Right. The next thing is to raise awareness and make sure that people know. So, for instance, giving talks like this, and I know I may be sort of largely talking to the choir, as it were. But so this is why some of you all know, I'm sure, quite early in this game, I wrote a non-technical book. So I do recommend, and it's got a lovely foreword by Brian May, who I met on a mountain once. And so do read the book. It's quite short and easy to read. It is, and this is very important. I designed it to be understandable and interesting, not just to the likes of professional amateur astronomers, but to all, your mum and your auntie and your hairdresser. Everybody should know. Attached to that, I've done various. This is my website that somebody mentioned earlier. I ran a live YouTube event in which I got a whole bunch of people to argue about the issues. It was terribly interesting, and it's still there. You either go to my website or the website of the Astronomical Society of Edinburgh, who hosted the event. So that's what I've been doing, my book and YouTube events and so on. Roberto Trotta in Italy did an absolutely fascinating thing. He put on a live sort of multimedia show that was a kind of play about a dystopian future in which you can't see the sky for satellites. It was called Libra, and the first performance was in Miramare Castle, just outside Trieste. But it's going to go on tour, so watch out for that. It is absolutely fascinating. Max Alexander, who's a photographer who specializes in working with scientists, at the moment is actually working on a major new photographic exhibition. Now, I mean, I think the sort of thing Max does, not just pictures on a wall, but something more like this, that could be sort of a giant sort of triptych of pictures, and it's about the junk problem. It's called Waste in Space. So here's a glove that's still floating out there somewhere. This is a hole punched in the solar panel of the Space Telescope by a small piece of debris. This is Max's idea to show what 20,000 tons of rubbish actually looks like. Okay, and now you imagine that up there flying in space. There is a Facebook group if you fancy joining it. Now at the moment it's a private group, but there's an associated public website, and that's called Action Against Satellite Light Pollution. So that's certainly something I recommend. Okay. Last but not least, because I think this is the most important of the possible approaches, regulate. Make some rules, improve the rules. There are rules in space. We've had the Outer Space Treaty since the 1960s, and it's still very important and it should not be thrown away. But we've got to build on it to build better, newer rules to deal with the new problems that are happening now, satellite light pollution and junk. So I think everybody knows this, but it's very hard getting there. There's some a sort of equivalent of SAGE in the US is called JASON. It's a sort of body of wise scientists who write reports for the government. So they were asked to write a report on satellite constellations and their possible problems. And there's all sorts of wonderful things in that report. But this is my favorite quote. A company who wanted to launch a dump truck full of sand into the same orbit as the International Space Station would have no formal barriers to doing so in many countries around the world. Now, as far as I know, there are no plans to launch a dump truck full of sand, but the fact that you might not be able to stop someone doing that if they wanted to is kind of the point. So as I said, there are regulations, but it's an incomplete set. So I hope this isn't too sort of detailed and tedious, but I think it's quite important. This is my sort of regulation scorecard. So the broad principles of how to behave in space are quite well set by the Outer Space Treaty. Getting permission to launch is very well controlled and licensed in most countries. The way you use the radio spectrum is quite well regulated through an international body called the ITU. And you have to be very careful about interference between satellites in geostationary orbit. So that's all the good stuff. Then we get down to liability. If somebody crashes into somebody else, whose fault is it? Who can sue who? Does somebody have to pay? What are the laws? This is, according to the Outer Space Treaty and its successors, you have to pursue this through diplomatic channels. There's no way, if a piece of rubbish from a Russian company falls through my roof, I cannot sue that Russian company myself. I have to go to my government and get the government to speak to the Russian government, and the Russian government speak to that company. It's supposed to be done through diplomatic channels, and it's extremely unsatisfactory. And it's only ever worked once. The Canadians did extract some money from the Russians from a radioactive satellite that landed in northern Canada, but it's only ever worked once. Keeping the debris, the junk down, there are some good guidelines, but that's exactly what they are. They're guidelines, they're not rules. There's no sanctions, there's no punishments for doing bad things. The whole advertising thing, in some countries there are laws saying no, and there are other countries saying, yeah, whatever. Yeah, so it's that's very mixed. And all these new things, atmospheric pollution from the rocket launches themselves, sky pollution that we've been talking about, interference of one satellite with another trying to beam down to ground. This is very poorly understood and very poorly regulated. And there are some legal challenges underway. It's all getting quite interesting. So in a way, a lot of this reminds me of the law of the sea. Now, I don't know if some of you may be old enough, I certainly am, to remember Cod Wars. Okay, now, originally on the sea, in the sort of 17th, 18th, 19th century, the idea on the sea was that everybody controlled a little coastal strip of water around their own country. And then out on the open seas, it was fair game. It was known, it was the policy of open seas or the freedom of the seas or something like that. It was kind of, nobody can tell you what to do. It's open for everybody to use equally. And that was the philosophy. Whereas you get too close, so that's a bit like airspace for us, whereas outer space is supposed to be free for all. It's exactly the same. So that worked well for a long time until the middle of the 20th century and onwards. It got worse and worse. So basically people got better at fishing and people were used to fishing in a certain spot, and others turned up and started fishing their fish, and they go, what? No. And then there were disputes over mineral rights. The US started saying, I think we lay claim to the whole of our continental shelf. It was really getting quite nasty. So during the 1970s, there was a big shake-up of the international law of the sea. It took 10 years to do. But out of that came new international regulatory authorities, and things got a lot better. They're not perfect now because people are still arguing about deep seabed mining, but they're a lot better than they might have been. And as I said, with Cod Wars, Britain and Iceland almost came to actual physical blows. So my guess is that sort of transformation to the law of the sea is what is going to happen to space. So it will happen. So the only question and the worry is that this change in the satellite population is happening so fast that everything may be, pardon my French, completely buggered up before we've got those new rules in place. So that's the worry, and that's all I've got to say for you. So you kind of, if you like, concentrate on the optimistic first bit. Study of the sky is really important. We're worthwhile to society, but there are some serious threatening problems. And that's the end of my story. Thank you.
Well, thank you very much, Andy. Yes, it was, I have to say, quite sobering talk, but I think a very important topic, and I certainly, for myself, I've got a slightly sore neck from nodding along at various points in agreement. We'll take questions as they come in, but the graph you had of space debris, that is something that I've been following, because the graph you put up, there's a bit of a jump in the 80s. And when I was doing solar physics with John Brown and Alec McKinnon at Glasgow Uni, and I think it was in the 90s, it would be in the 90s, I was working on some data that came from a solar satellite called P78-1. I think 78 might be the year it was launched. And I thought, well, this is interesting data. And I said, what's the satellite doing now? And there's a bit of laughter, and someone said, oh, well, the US Air Force shot it down. So, and solar physicists were not happy that the US Air Force shot down one of their satellites. But apparently it was an F-15 fighter jet that shot it down. And that was one of the first contributions to this jumps in space debris. So yeah, to be fair, the US Air Force also launched the satellite for them. So, you know, maybe that was fair enough. So, okay, so questions. Okay, so first question is from Laura. So Laura's on video.
Hello. I was wondering, is there much evidence of corporate donations influencing what we currently have in space? So for instance, you were mentioning soft drink companies. I wasn't sure if it was a company that was working with soft drinks to advertise them, or if it was soft drinks that were actively seeking to be put out in the sky. But yeah, basically, because I know SpaceX is private, but it's also mixed with NASA, which is governmental, I think. So,
well, it's not mixed. Yeah. So your first question is a very interesting one. Did the soft drink company start the idea, or was it the company who came to them? And I don't know the answer, I'm afraid. My guess is the second way, that there was a clever little company who came to the soft drinks company, but I don't know. SpaceX are private, and they can get and raise money however they like. They're not part of NASA, as it were, but they take NASA contracts. And for me, actually, this is one of the most frustrating things about how annoying Starlink is, because mostly I think SpaceX is a very good company in that. Whereas Richard Branson and Jeff Bezos are just playing rich boys going into space, SpaceX are doing real work. They take astronauts up to the space station. They've launched useful satellites. You know, but they're doing it by taking contracts. So it's just NASA and others outsourcing. They want something, and they pay SpaceX to do it for them. And generally, they do that sort of work very well. So to me, and there's nothing wrong with that, you know, and the idea of commercial space is good, but obviously there are dangers in that, you know, and I think this somewhat crazy idea of Starlink is one of those.
Right, thank you. All right.
Okay, so any other questions coming in?
I see, by the way, David's answered my question about Albireo. It is Beta Cygni.
Beta Cygni, yes.
Can I ask a question?
Of course, when you go down.
I was just wondering, is there no policy in place for people that put satellites into space? Once the satellite's reached the end of its life, it's up to their responsibility to get rid of it?
No, that's a very good point, because there is no such policy, and there jolly well ought to be. At the moment, you know, and the trouble is, it's a typical commercial problem when you take a commercial attitude. So let me backtrack a bit. In the past, there was few enough objects that people didn't worry about it much. They just thought, yeah, let it die, it's fine. It's now becoming a real issue because space is more crowded. But of course, if you're a commercial company, you don't want to spend money you don't have to. So it's not going to happen spontaneously. There has to be a rule that says take it away. Interestingly, there are other companies who are looking forward to this and trying to make a business out of, we'll come and get your satellite and take it away. So Astroscale is one of those. It's a joint American, British, Japanese company, but they're very interesting people.
Yeah, can I just say, I think when they're costing up these kind of missions, they should be costing in the cost of getting rid of it at the end when its lifetime is over. I mean, we have a similar problem because I work at university. We have a similar problem. People come in, they do their research, they're buying all these drugs, and then they disappear, and we're left to get rid of all their waste. So what we're going to do is we're going to, when they come in with their grant money, we take a portion of that to clean up after them once they're finished. I think it would be good to have that kind of policy.
Yeah, no, absolutely would. Now, at the moment, the closest there is that there's a guideline, and it's not a strict rule, though I said there's no sanctions, but there's a guideline saying at the end of a satellite's life, you should sort of park it in a less dangerous orbit. Either take it higher up or take it lower down where it will drift down and burn up. And actually, so firstly, those guidelines have to turn into real rules. And secondly, you have to actually arrange to get rid of things rather than just parking them somewhere, I think. But yeah, it's a very important issue. Thank you for that.
Okay, thanks. So I see the Kessler effect is starting to occur in the chat window. So we've got loads more questions coming in. From YouTube, Ariok53, I hope I pronounced that right, says that international agreements and legislation seem to be the only solution to this. Is there a transnational astronomical or scientific organization which could lobby on an international scale?
Well, that would be the International Astronomical Union. So that I've got to answer this a little bit delicately because the IAU, the International Astronomical Union, has been working hard on this. They set up working groups and conferences for people to talk about the issue. But my feeling is that they've been a bit too soft. They don't see it as their job to produce the regulations. So they've concentrated on the engage and mitigate part, working with the companies to try and ameliorate problems or understand where the satellites are going to be, and so on. The trouble on the regulation front, and this is very similar in some ways to climate change. It's all done nationally, unless nations agree to set up an international body for a specific purpose. Like we did with the Geneva Convention, for instance. But to do that, nation states have to cede their power to some new organization. So in terms of global, so there's a UN committee, but again, it's a bit of a talking shop. But it's very hard to get there because nation states are very protective of their own business and their own companies and so on. But it's sorry, it's a bit of a complicated answer, but yes and no is the answer.
Yes, I can well imagine getting international cooperation at that scale is very difficult. But let's not start to think about interplanetary or interstellar cooperation. So I've got a question here from Karen McLaurin. I see Karen is actually here in Zoom. Karen, would you like to ask the question yourself? If so, you can start your audio or video. If not, I'll ask it for you.
Oh, I didn't know I could unmute myself.
Oh yes, we let people speak in this society.
I wanted to ask if there's any space debris that's big enough to cause a dinosaur level disaster if it hit Earth.
I'm very pleased, just for a change, to answer optimistically, because the answer is no. None of the things that are up there are really big enough or moving fast enough to make something that bad. But it could be, but it would be pretty bad. Something actually landing, on a building. More to the point, there could be pieces on the way down which will crash into aircraft. So it could easily be something where you kill hundreds of people. So that's something that people are seriously worried about now. But more to the point is, if the use of space commercially, civilly, and for the military as well is all very important, and we want all that, as well as doing science, of course, with the things like the Hubble Space Telescope. So the real point is it's self-defeating, because we want commercial activity in space, but the more there is, the more it's kind of soiling its own nest, if you see what I mean. And it could become a dangerous place to have any satellite if we're not careful. But actually, a dinosaur killing level event, then no, someone's not big enough for that. I see David has put in the chat, unless someone has secretly built a Death Star. Yes, well, you never know, but somebody would spot it.
Yeah. Have you ever looked at a photograph and thought to yourself, that's not a moon? Okay. So, Laura, you have another question.
Yes, this one's more about the first part of the talk, where you were talking about the usefulness of astronomy. And I found that when discussing that with people, the biggest objection I get is for interplanetary travel, especially manned, or having colonies on Mars and such. And usually the argument that I hear is, why don't we prioritize people on Earth before putting people on other planets?
Yes, well, I would certainly take that point of view. I mean, and I know you're thinking about Elon Musk in particular and his Martian plans. And, I think what people say, I'm not sure this is really true, is that he sees Starlink as a sort of cash cow, as helping to fund his grand ambitions to go to Mars. But yes, I think that's very utopian and foolish, and we should be fixing things on Earth, and not going to Mars in too much of a hurry. Yeah, that's definitely my feeling. So did that answer your question?
Yeah, I was just asking for your opinion, basically. But for instance, you get people like me who love Star Trek and love the idea of interplanetary travel, but as you said, it's not the emergency right now to get to that. But do you think at some point in the future, if things were better here, it could be a good option, or do you think it's just frivolous on the long term?
In some ways, I think moving to Mars to colonize Mars is absurdly under-ambitious. So Mars is a daft place to live, as is the moon. It's very inhospitable, very hard to get there, very hard to set up. Why not just make the Earth nicer? It's just very, very silly. What might happen one day is you could have a mass migration, and this would be a long way in the future because technology is not there, but you could build some giant arcs. So it's a bit like sort of space versions of the Eden project. I don't know if you've been to Cornwall, but and you could have 100,000 people in one of these arcs with all the plants and the oxygen and whatever they need to live, and set off and drift over hundreds of years until you reach Deneb or something, right? And then start again when you find an M-class planet, as we say. That I do believe may happen one day, but I actually think colonizing Mars and trying to terraform Mars and all that sort of thing is really pretty daft. That's my gut instinct. And yes, I can see you are currently sitting in the control room at Starship Enterprise.
Yes.
I was trying to remember which generation that one is. I think that's
Next Generation.
Next Generation. That's the Captain Luke Picard one, yeah? Indeed,
yeah. But yeah, that sounds good as well. I agree. Like, it does sound better than colonizing Mars. It does seem a bit hopeless. So thank you.
Yeah, I've got a question that was prompted by something you said at the beginning. There's a science fiction story I remember reading years ago about a civilization that's not unlike ours, but it grows up on a cloudy planet where you can never see the stars or the sun, just that it gets light and dark. And it's very interesting. I forget who wrote that story, but it's quite thought-provoking. Does it concern you that maybe the future generations living in the Earth might not be able to see the night sky, just from the point of view of being a human being and connected to stars? Since you mentioned agriculture, but we evolved under the stars and the sun and the moon. Does that concern you that that's a possibility that we might lose that? Oh, you seem to be muted.
Sorry. Yes, I had temporarily muted. Yeah, I do find that quite disturbing. And now, of course, I thought about this when I was writing my book in particular, and this business of how important astronomy has been to the development of science and technology, and thinking, well, what would have happened if we'd been living on Venus, and we'd never seen the stars, and would it be that we'd have made all these scientific discoveries eventually another way, or are there some things we'd never have understood? And I don't know the answer to that question, and of course, as relevant to the question of what future scientific discoveries or perspectives on the universe, cultural changes might we miss out on if we can't see the stars in the future. So I don't know for sure. It's very hard to be quite rational about this, but my gut instinct is it's got to be a bad thing.
Yeah, that's my feeling too. Oh, we've got another question coming from YouTube. Scott Oakley asks, you talked a lot about the benefits of astronomy to our society. How has funding for astronomy fared over time, and how is it doing currently? Okay, so I would say it's funding for astronomy over history. It's gone in kind of two jumps. During the sort of 17th, 18th, 19th century, it sort of took a jump up from what it had been in ancient history because of navigation and timekeeping. So governments did care about this stuff. So they did fund observatories. But compared to modern science, it's relatively small beer. So astronomy has gone along since the Second World War, suddenly started getting a lot more money along with all the rest of science because, crudely speaking, because of radar and the bomb and other things. So it's horrible to think about, but it was because of the war that governments realized that understanding science and technology was very important. And they did kind of work out that this doesn't just mean if you want to make better bombs, although obviously lots of governments cared about that, but they realized that to be competitive in a modern world, it kind of really matters. So, after the Second World War, the funding of all science basically took a huge jump up, and then flattened at about sort of 1 or 2% of GDP. So there's some natural limit to which most of the people running the economy are saying, nah, that's enough. It's about, do you invest in clever things for the future? So astronomy was just a kind of carried along by the coattails on that. And as I said, many people understood this point that astronomy was not just a kind of romantic exercise, but was all part of understanding physics and technology. Right. So then, crudely speaking, it's kind of jumped up in the 19th century and then jumped up in the second half of the 20th century, and it's been kind of toddling along flat ever since. But since then, in more detail, undoubtedly over the last few decades, astronomy has fared slightly worse than most of the other big sciences, medicine, biology, and so on. And you might argue correctly so, this is very difficult. Well, that's kind of fine tuning, but a bit of a long answer, but it's quite an interesting question.
So basically, for the last few decades, it's been fairly flat, but maybe slightly going down. And there was another in the UK. There was a jump up with the Labour government in the late 90s, and then down again in the austerity era, just like you might guess, basically.
Yes, thanks. So I think I've read all the questions we've got. Are there any more questions here in Zoom that you'd like to ask Andy?
Yes, Andrew.
On you go.
Andy, thank you very much for that very thought-provoking talk, and thank you for the Lisa Pathfinder shout out. It's appreciated. You speaking of the space junk, do you think there's any hope for a bin lorry equivalent to be or bin lorry equivalents to be deployed in the low Earth atmosphere or orbits? Sorry. To collect and reduce the number of pieces of debris that are going around?
Well, it's a good question. I think let's separate that into two parts. I think the idea of collecting the big bits, like dead satellites, there are people working on that, like Astroscale, for instance, and the technology is looking pretty good to do that. And the main obstacles are legal, because there's no law of salvage in space. You know, you can't just go up and say, I'm grabbing that and taking it, because it's no use to anybody. It still belongs to the people who launched it. So that has to be sorted out. Okay, but big things, but just that technically big things can be collected. I'm sure that will happen. But how you actually collect all the millions of bits of tiny junk, that's much harder. I don't know how people have talked about, you know, drag nets and so on, and none of it's very convincing. So I think that means we can't let it develop as it goes along and keep taking away the junk. But the small bits of junk we've just stuck with, and we've got to stop making it. Otherwise, because I think the small bits are just going to be almost impossible to remove. They move really fast. Here's a little scary sort of statistic for you to close up. Sorry to end on a depressing note. It's quite impressive. You know, the average orbital speed is something like 10 kilometers a second, and there's the relative speed of 2 bits. Now, if something as big as your fist could destroy a satellite, right? Moving at 10 kilometers a second. So you carry an enormous amount of energy moving at that speed. But something like that, if it's just reflecting sunlight, if it's 10 kilometers away, you'd need a pair of binoculars to see it. If you just stared out from your spacecraft and looked, you wouldn't see it. So something could be 10 kilometers away, more or less invisible, and 1 second later, hit you. So I think that that is, to me, is incredibly impressive and very, very scary, and that's why it's so important. It's very hard to beat.
Yes.
Yeah, that's a sobering thought.
Indeed, a sobering thought. Well, I've just see Scott on YouTube as thank you for your talk and the detailed answer to the question, and actually many other positive comments coming in that you probably see in the chat in Zoom as well. But can I just thank you again, Andy? That's a really thought-provoking talk, very clear, informative, and really thank you again for doing it. So if you could show Andy our appreciation. I know we can't really do it in a real lecture room, but thank you very much.
My pleasure. And yes, I wish I was with you, but there we go.
Yeah, well, in the future, hopefully you can come over to Glasgow in person, and we will take you up to the pub afterwards before you open your train back. So, but for now, that was excellent. Thanks again, Andy.
Thank you. My pleasure.
Thank you. Great. Andrew, remember the...
Oh, yes, sorry. We're not quite finished yet. So don't rush off. And we have something for you. Unfortunately, we can't give it to you. So, but David will present it to you virtually.
Yes, this is something we do annually at the Tannahill Lecture.
Ooh.
It's a commemorative medal presented on honour of Sir Thomas Tannahill, who on his death, on his passing back in 2007, I think it was, left a bequest to the Society, a significant bequest, with the terms that it should help to promote astronomy in the west of Scotland. So this is a... Hopefully you can see it. That's a good enough angle to see.
Is that a picture of the man himself then?
Yes, it is. Yes, yes.
Jolly good.
Past recipients of the medal have included Tom Bowles, Alan Chapman, Jocelyn Bell Burnell, Professor David Southwood, Sir Alfred Wolfendale. So,
I mean, good company.
Yes, what we'll do is if we can get an address from you, to send it to you.
Yep.
I think I have an address on one of the emails.
Yeah. So
you want to send it to?
Send it to the Royal Observatory, and I'll get it there. So Royal Observatory, Blackford Hill.
That's fine. I'll get that out to you.
Fantastic. Thank you very much.
Okay.
Yes, most deserved. Okay, well, thank you very much. We'll be closing on the YouTube stream in a moment. Remember, if you're not a member of the Society, you're very welcome to join. Just go to our website, theasg.org.uk. Be very welcome here. Thanks a lot, Andy, and thanks for everyone for coming along tonight.
My pleasure.
Thank you. Excellent.
Thanks, Andy. Thanks. Thank you.
Bye bye. So I'll disappear now, and
Okay.
see you all one day in reality.
Hopefully, yes.
Okay.
Thank you. Bye.
Okay. Bye for now. Bye
Thank
bye.
you.